In applications in math and physics, there are certain quantities that are completely determined by their magnitudes. Things like mass or area, temperatures. Those quantities we call scalars. They're just plain old numbers. Other quantities have both a magnitude and a direction, like the velocity of an airplane or the force applied to an object. And those quantities we call vectors. And we use directed line segments to represent a vector. So let me draw what we use to represent a vector, something that looks like this. We have an initial point, and we have a terminal point. And I will label this initial point A and the terminal point B. So I would call that the vector AB. Sometimes we can use a single letter to represent the vector, like I could call this the vector V. And those two things would be equal. You'll notice when you're reading in textbooks that you don't see the little arrow over the V because you see that the vectors are written in bold. In textbooks, you'll see them in bold. But when we write them, handwrite them, we'll put an arrow over it so people can tell that we're talking about a vector. When representing vectors, two vectors are equal. If and only if their magnitudes and directions are the same. If they have the same magnitude and direction. So for example, let me just separate this here. If we look at these two vectors, this vector here and this vector here. Now I tried to draw them the same length because the length represents their magnitude, but they aren't in the same direction, so these would not be equal. Or this vector and this vector. Now they're both heading in the same direction, but their lengths are different, which means their magnitudes are different. So again, they're not equal. Even this vector here, suppose I have this vector in this direction and this vector in this direction. Now they look parallel, but notice one is going in this direction to the upper right, and this one's going to the lower left. So even if their magnitudes were the same, and in fact, if I drew those the same length, their magnitudes would be equal, they are not equal vectors. Keep in mind that these are directed line segments. They are not raised. For example, if these were raised, they would be going off in this direction forever, but that is not the case. It's just telling you the direction of the line segment. The line segment starts here and ends here and goes in that direction. It doesn't imply it continues forever. So equal vectors would be something that looks like this. This vector and this vector. Exactly the same magnitude in exactly the same direction. Those would be equal. Let's continue. Sometimes we want to add vectors. Suppose I draw this vector u right here, and I'll make this vector v about that long. Suppose we wanted now to find u plus v. Now I'm going to draw these two vectors. I'll start with U. So I can move this vector over here, making sure I keep that same magnitude and direction. So I'll do my best, let's see, about that long, right? So there's my vector U. And vector V, about this long, I'm in this direction, right? That looks like about vector V. And we would say this is their sum. Start with the initial point of the first vector and finish with the terminal point of the last vector. And here is our result. And it's called the resultant vector. So this is U plus V right here. And the sum of the vectors is a resultant vector. There is another way that sometimes people find the resultant vector, and that is by building a parallelogram. If in fact we took these two vectors and put the initial points at the same place, you might be able to hear my dog barking. So we'll draw these. So here's my vector U and here's my vector V. If I now draw a parallelogram, so I'll draw this side parallel to this one and this side parallel to this one, and we draw the vector that is the diagonal. Oop, I missed it a little bit. That would be the resultant vector, and you'll notice those are equal vectors. They have the same length and they go in the same direction. Let's add these vectors. I already have U and V and W drawn, and I put it on graph paper so it'll be a little bit easier for me to maintain the size of the vectors and the directions of the vectors. So suppose the directions were defined, the sum of the vectors U plus V plus W. Now I'm just going to create a path, meaning I'm going to start with the initial point of the first vector and draw the vector, and from the terminal point of that vector I'll put the initial point of the second vector. So here's what I mean. Let's start with this vector U. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units across. So when I draw the vector U, I'll start it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my vector U. There's the initial point, here's the terminal point. So the initial point of the next vector will start right here. Notice it's going down 3 units, so we'll do that. Here's my vector V. Now here's my vector W, so the initial point will go right here at the terminal point of the previous vector. And I'm going to draw it the same way. Let's see. There's my vector W. So the resultant vector is the vector that I get if I start at the initial point of the first one and finish at the terminal point of the last one. So here is the sum of U plus V plus W. Let's look at what the sum would be, the resultant vector would be, if we added them in a different order. What if I had said, let's find V plus U plus W. Let's create that sum. So we'll do the same thing. V, I've made it go away. Let's see, I'll leave it there so we can see it a little bit longer. We're going to start with the vector V. And let's see, it starts here and goes down 3. Here's my vector v. Now I'm going to add u. Here's the vector u. And then now I'll add w. And so my resultant vector would be right here, coming down this direction. And if you compare these two vectors, they are exactly the same length, going in exactly the same direction. And that's because we say that the addition of vectors is commutative. So in fact, you can add vectors in any order and get the same result. So here was our sum, and notice again, same length in the same direction. Now, I like to think of vectors sometimes when I'm figuring out, well, what are they good for? I think about an object that's on the ground, and I have 3 different people pulling on it. Some are pulling a little bit harder than others, and I'm putting it on the ground so that we'll just be talking about 2 dimensions. The object will be pulled this direction and this direction and this direction. But I will tell you, vectors are wonderful even if you're in 3 dimensions. But let's see, if we had an object here and somebody was pulling it lightly this direction, somebody else pulling it harder this way, the magnitude of the vector is telling you how hard they're pulling, and this person is pulling even harder. The question is, what's the result? Where will this object go? Will it go in this direction or this direction? Will it come down this way? Maybe you have a sense, since it's being pulled harder in this direction, it's somehow going to go in that direction. But let's mathematically figure out what it would look like. What's the result? And it would come from just adding these vectors together. I'll call this vector u, this vector v, and this vector w. And we just saw on the previous one that you can add them in any order. So let's start with u. Let's see, how many units did I go? 1, 2, 3, 4, 5, 6, 7. So I'm going to start here and go 1, 2, 3, 4, 5, 6, 7. So there's the vector u. Now I'm going to add v. V, let's see, I went down 3 and over 1. So we'll go down 3 and over 1. So here is our vector v, right here. Now our vector w is going in this direction. How many units? 1, 2, 3, 4, 5. So from here, I'm going to go 5 units this direction. And my resultant vector, now that was w. My resultant vector is this, starting here and heading in that direction. So the result is this object that's being pulled in 3 different directions would head off in this direction. Not as far as this person may want it to go, because we have people pulling in other directions, but the result is the object would move in this direction. Let's do a little bit more. Suppose we talk about a vector being multiplied by a scalar. So I'm going to let this be the vector v. So there's our vector v. What happens if we take our vector v and we multiply it by 2? In other words, I would like the vector that is 2 times v. Well, I'll tell you, it doesn't change the direction at all, but it does change the magnitude. It's going to make it twice as long. So if I'm going to draw a vector that is 2v, I'm going to look at that vector and go in exactly the same direction. That looks like about 1v, and I'm going to extend it and go twice as far, and there is the vector 2v. If I wanted the vector that was, say, 1/3 v. Again, I start in the same direction, so I'm going to start anywhere, head in the same direction, but now it's just 1/3 as long. So maybe like this. There's our vector that is 1/3 v. How about if I multiply by -1? Well, multiplying by -1 doesn't change the magnitude at all, but it just does change the direction. It will be exactly this magnitude, but instead of going up and to the right, it will go down and to the left. So the vector will be exactly the same length, in exactly the same angle, but its direction will be 180 degrees different. So of course I could multiply this by -3, +10, -1700, and find the relative sizes of the new vectors. So that brings me to being able to add something like this. Suppose we have these two vectors. I'll make this the vector A, and I'll make this the vector, we'll make it not too steep, going in this direction, and I'll make this the vector B. I would like to see the vector that is 4A minus B. So we're going to find the resultant vector that is 4A minus B. So let's start with this. We're going to multiply it by 4. That means I have this particular vector. I'm going to draw it down here, and I'm going to make it 4 times as long. So that looks like 1, 2, 3, 4. So there's my vector that is 4A. Now what you need to know is subtracting vectors is really just the same as adding the opposite. So I could think of this as 4A plus -b. So let me now add -b. So it's this vector going 180 degrees in the other direction. So let me move this down here. It's not very steep, going in this direction. Now it's headed this way. This is -b. So the result is this vector. Start at the initial point of the first vector, finish at the terminal point of my last vector, and this is 4A minus B. I hope you'll have a chance to add and subtract some vectors geometrically.